Okay, good evening everybody. My name's Andy Stevenson. I'm the chair of the Teesside panel of the Institution of Mechanical Engineers based in North East England, and I'm pleased to welcome you to our third Tech Talk event, this being the second one that we've held via webinar. We've got quite a few people online tonight, so thank you very much for joining us. So the format for tonight is two short 15 to 20-minute presentations, each followed by a brief Q&A session. You can submit questions to me via the Q&A box on the bottom right-hand side of the WebEx screen. Our speakers tonight are Nick Contopoulos, the Chief Operating Officer at Anemoi Marine Technologies, who's going to talk about their work on Flettner Rotors. And then we've got Siobhan Doole, an analysis engineer from JDR Cables, who's going to talk about the design and development of subsea cables. I've personally worked with both companies. They've got some really interesting products and innovations, so it should be two very interesting talks. So just a bit of a reminder, we're always interested in volunteers, so if you'd like to get involved in giving a short talk at a future event on any mechanical engineering based topic, please get in touch with myself via the email address shown or via the IMechE's Near You website. So we have a fourth Tech Talk event coming up on the 27th of May at 5:15, which is going to be jointly hosted with the Institution of Diesel and Gas Turbine Engineers. And that's going to cover a talk on the Subsea offshore wind farm and the Teesside net zero carbon capture and storage project. So please look out for details of that. Finally, tonight's webinar is being recorded and will be available to view via the IMechE YouTube channel. Okay, so thank you very much for coming along and for listening. I will pass across to Nick, who's going to get the first talk underway. So over to you, Nick.
Thanks for the introduction, Andy. So, good afternoon, ladies and gentlemen. As Andy introduced me, my name is Nick Contopoulos, founder at Anemoi, and I'm now in the role of Chief Operating Officer with a focus to help the team commercialise our Flettner rotor technology. So, for those of you who don't know Anemoi, Anemoi is a British startup specialising in technology development in the marine sector. Anemoi have developed Flettner rotor systems that harness the renewable power of the wind to provide commercial vessels with auxiliary propulsion, resulting in the reduction of fuel consumption and harmful emissions. So today I've got the great pleasure in giving a brief introduction to Anemoi as a company and the journey we've been on, Anemoi's rotor technology, and the performance benefits of Anemoi's systems in terms of fuel and emission reduction. So starting with some brief introduction and history about the company, Anemoi was established to develop green technology that would have a positive impact on the shipping industry. We've evolved over time through the successful development and testing of Flettner rotor systems, including land-based prototypes and successful pilot installations on board globally trading vessels. Following the delivery of the MV Afros, a 64,000 weight bulk carrier in 2018, there's been a huge amount of inbound interest in our technology. And we're now working with a number of industry stakeholders to develop projects that will see the technology rolled out both on new builds and retrofits, helping the industry work towards fuel and emission reduction targets. The MV Afros pilot vessel has received 3 global awards since delivery, including Ship of the Year in the 2018 Lloyd's List Greek Shipping Awards and the 2019 Green for Sea Dry Bulk Operator Award in Athens. As you can see there in the top left corner, our rotors have accumulated nearly 230 million revolutions during operation since delivery in 2018. So the video will play after this slide. I've got some help from our friends at IMechE to play the video. So hopefully this will go smoothly now. So in this video clip, you'll see a demonstration of the rotors operating at sea. Hopefully you can all see that and it's not too laggy, where they are fixed down to the ship's deck, followed by a demonstration of the rotors being moved in port using the Anemoi rail deployment system, which is the image you can see now. This enables the rotors to be positioned clear of cargo operations when the ship is entering port or at anchorage. So this part of the clip obviously shows the ship discharging its cargo from the starboard side using the ship's gear, and the rotors are moved well clear of any operations. So we'll move shortly on to the next slide now. Thank you. So a little bit about the Flettner rotor and the Magnus effect, the principles. For those of you who are not familiar with Flettner rotors or the Magnus effect, please see the right-hand side of this slide. With wind coming from the starboard or right-hand side of the vessel, rotors are turned in an anti-clockwise direction, accelerating the airflow forward of the rotor, creating a low-pressure region, decelerating the airflow aft or behind the rotor, creating a high-pressure region. The pressure differential produces thrust along the length of the rotor in the forward direction of the vessel, and the thrust force is transferred directly to the ship's hull, like a conventional sail, enabling a net reduction in engine power or an increase in vessel speed. So the Anemoi rotor system and its general layout on a ship. This graphic here shows a typical bulk carrier vessel with deployment system. So this typical layout of Anemoi equipment would include Anemoi rotors and deployment system, which can be seen fitted on the deck, the control system and user interface located in the bridge, electrical and control hardware located in the engine room, and to fit these pieces of equipment on board the ship, there's integration and preparation work required, typically structural foundations and hard points to fix the rotors to, a rail system when installing on a bulk carrier, typically, and mechanical and electrical fit-out of power and data cables. The graphic on the right shows the Anemoi rotor, and this typically comprises of a steel tower structure inside the rotor, which is shown in white in the diagram, the composite rotor skin, which is shown in blue on a blue background, which we'll do something about for the next presentation, but you can see there the cylindrical rotor part. This is the rotating cylinder that you saw in the video earlier. The upper bearing system at the top of the tower that comprises of the roller thrust bearing fitted to the top of the tower. This is the interface between the composite rotor and the tower structure and restrains the rotor both axially and radially. The lower bearing system restrains the rotor radially. The electrical drive system is integrated with the lower bearing at the base of the rotor. So Anemoi's composite rotor. So the rotating part is a highly engineered composite component, and as seen in the video, is defined as the rotating cylinder part. It is designed for severe combined load cases, referenced from class rules. For example, survival conditions of 63 meter per second winds, combined with plus or minus 1 g vertical acceleration, plus or minus 0.5 g horizontal acceleration with a combined 30-degree heel angle. So quite severe load cases there, similar to the ship's crane rules. The rotor, as you can imagine, is a major cost component of the system, and we are using our operational data from the pilot installations to inform the continuous improvement of the rotor design and develop our go-to-market products. Future rotor design and manufacturing methods will be focused on scalability and volume production for rollout. So moving on to the Anemoi electrical and control system. The Anemoi control system and user interface provides autonomous operation of the rotor and will self-trim RPM as a function of wind speed and direction, with little to no crew interaction required. This is very important for the owners. Power required during operation is directly correlated to the RPM. Therefore, the input load is variable. The mean input is approximately 25% of the rated power of the electric motors. Anemoi systems can be used in conjunction with other energy-saving technologies. For example, on the pilot installation, we fitted VFDs on all engine room pumps and fans so that we could reduce the generator headroom and create additional space to operate the system on a single generator, removing the need to operate a second generator for the rotors. Some of the key considerations for particularly tankers and bulkers, but also other vessels like Rotors. These key considerations vary from vessel type to vessel type, and Anemoi rotors can be coupled with a range of deployment systems to overcome constraints associated with port and cargo operations. So starting with the fixed deployment system, where there is neither cargo handling or air draft constraints. Typically on tankers and ro-ro vessels, the Anemoi rotors can simply be fixed to the deck of the vessel. The rail deployment system, developed for bulk carriers, as shown in the video earlier, has been developed to allow the rotors to be moved to clear all port operations and not affect the vessel's business in port. The folding system that we have developed allows the rotors to be lowered to the horizontal and is suited to vessels with air draft or other operational constraints. So although we offer a broad range of deployment system options for the various parts of the shipping market, the Anemoi rotors are designed, have a common design and have the same form for each installation. So once the rotors have been installed, we have the key installation and commissioning requirements. As mentioned earlier, the integration work primarily consists of structural integration of foundations and rail system, electrical and mechanical installation and integration in the engine room and bridge. And typically, the installation equipment includes lifting and fixing the rotor down in one crane lift, in a single crane lift, so it can be done very quickly. Lifting and positioning the deployment system also can be a quick exercise, and functional testing of the software and dynamic balancing of the rotors prior to delivery. And all systems are inspected, surveyed and approved by class at all stages of the construction. So just quickly on maintenance and support. From our experience to date, maintenance costs have been relatively low, in part due to the simplicity of the machines and low component count. Annual inspections are carried out, timed with standard vessel survey, intermediate survey or special survey. Now, Anemoi's data analysis and data acquisition. So we have a sophisticated data acquisition system that transmits and records real-time data from ship to shore for analysis and performance verification. State-of-the-art data is also used for condition-based maintenance, optimization of control systems and overall system design. Anemoi's control system collects data in various areas of the ship, including the vessel dynamics and motions, environmental data, including wind speed, direction, temperature, humidity, etc., and engine room data, power data, and navigational data. Typically, we have and are recording 500 data channels in real time that can be monitored and analysed from the office. The graph that you can see here on the left just gives you an example of the rotors in operation. So the timeline there is approximately 6 hours, with the light green showing speed over ground and the darker green showing speed through water. Now, the black line shows when the rotors are switched on and off for periods of about 45 minutes to 1 hour. And you can see that every time the rotor is switched on, the vessel speed increases. Now, we've been running these tests for years now, so we have terabytes of data here showing the repeatable performance impact of the rotors on the ship. And typically on the MV Afros, the vessel increase in speed is in the region of 1 knot in favourable conditions. So reference projects, the MV Axios and the MV Afros. Starting with the Afros, as shown, the ship vessel has been operating for approximately 2.5 years, has visited over 40 ports without any delays to the vessel. Operational availability of the rotors since installation has been greater than 99%. This has been validated through our data. For clarity, this number means that when conditions are favourable, the rotors have operated more than 99% of the time. Moving to the MV Axios, Anemoi prepared the world's first wind-ready vessel, which is an 82,000 deadweight gearless Kamsarmax bulk carrier. This vessel is prepared to receive up to 8 rotors. So some discussion now about Anemoi's fuel saving assessment method and the fuel and emission reduction potential of the Anemoi system. So there's obviously many drivers, commercial and environmental, for adoption of technology like wind power, and the IMO is driving many of these regulations. So for those of you that are not familiar, the IMO, the International Maritime Organization, is the United Nations agency with the responsibility for the prevention of marine and atmospheric pollution of ships. Even though today's shipping is seen as the cleanest mode of transport for world trade, shipping is currently excluded from the Paris Agreement. The shipping industry accounts for approximately 3% of global emissions. However, this number could significantly increase by 2050 if the industry fails to act now. So the IMO have set targets that by 2050 they want to reduce the greenhouse gas emissions of ships by 50% compared with 2008 data. This aligns with the Paris Agreement goals and is part of the shipping industry's strategy to reducing harmful emissions and moving towards decarbonisation. So obviously from our perspective, where I'm sitting, harnessing the renewable power of the wind as an auxiliary ship propulsion can help the industry move in the right direction, and the technology is available today. So here is an example arrangement of 6 4-metre by 28-metre in length rotors fitted to a Newcastle-Max bulk carrier, which is 210,000 deadweight tonnes. There are many configurations with various rotor sizes that can be analysed, with rotors ranging up to 5-metre diameter and 35 metres in length currently. So for the purpose of this example and all the following slides in this analysis, the data is related to this configuration on this vessel type. So here's some numbers. So running this vessel through our model with the configuration fitted on the Newcastle Max, trading between Brazil and China, gives savings of 14.1% in fuel and emission reduction, which equates to over 1,600 tonnes of heavy fuel oil and over 5,000 tonnes of CO2 per year per ship. So in terms of the method and data analysis, Anemoi have developed a proprietary method for calculating fuel emission and financial savings. So our fuel saving assessment method is used to predict the fuel savings and is underpinned by the following data sets. Rotor thrust data set is obtained from our land-based testing facility in the northeast near Newcastle. The vessel data is provided by the owner typically, or other open source data sets or paid for data sets like Clarkson CNET or RightShip. The wind data set comes from the NASA MERA-2 data, which is global statistical wind data dating back to about 30 years. So there's a huge database there for wind data. And route data and AIS data is provided either from the ship owner or a third-party AIS data provider. So these data sets are overlaid and the numbers are crunched in our proprietary software to output fuel emission and financial savings. So the IMO introduced the global wind probability matrix for defining the probability of a vessel experiencing each wind speed and direction while sailing. So using this method for the configuration on the Newcastle Max gives an average fuel and emission saving of over 1,200 tonnes of fuel per year, heavy fuel oil, and over 3,900 tonnes of CO2 saved, equating to an average of 15.2% fuel saving over the course of the year. So this is one method that we use because it's understood by everybody and it's a mandated method through the IMO. But often we're asked to analyse specific routes. So just moving on now, this is the analysis of a specific route, usually requested by a customer, and the routes selected here are key commodity routes: Australia, China, and Brazil to China, often served by Newcastle Max vessels. So variables that can be addressed in the model include vessel routes, loading condition of the ship, vessel speed, and fuel type, among a number of other variables that can be assessed. So the results here show the savings in terms of fuel and emissions for each of those routes. And as you can see, the expected fuel and emission savings for the Tubarão to Qingdao route is 14.1%, equating to over 1,100 tonnes of heavy fuel oil saved per year and over 3,600 tonnes of CO2 per year. Averaging those two routes gives you an average saving of 13.3% per year. But you can see how the route is very important to the results in terms of the wind. So we're very sensitive to the route that the ships operate on. So as you can see here, and as you'd probably intuitively expect, the rotor performance varies with season. So just closing up now and wrapping up, Energy Efficiency Design Index. Regulation is driving innovation, although not as fast as we'd like. It is there, and it is forcing decisions for all the stakeholders in the industry. In the short term, regulations like the IMO's EEDI Phase 3 and more recently the plans for EEDI Phase 4 are forcing the industry to explore and adopt new and innovative solutions to achieve compliance, especially for larger vessels. This trend of incremental efficiency gains will continue to be driven into the medium and longer term by the IMO 2030 and 2050 targets. And this EEDI target also has a big impact on the ship designers and the shipyards who are now developing and designing ships today that will probably be built post 2025 when Phase 3 comes into force for many ship types. So it is on the agenda of shipyards and ship designers all across the world at this moment to try and find solutions that can help them comply with future regulation. So thanks everyone for listening, and look forward to any questions that you may have.
Excellent. Thanks very much for that, Nick. That was really interesting. A couple of quick questions that have come through from some of our listeners. So from a technical perspective, someone's asking if the wind direction has to be in a certain orientation relative to the vessel motions for the system to work. I'm assuming that's tied into trade winds. Is that right?
Yeah, typically the 30 degrees forward of the ship and 30 degrees after the ship, so 15 degrees plus 15 degrees forward and 15 degrees plus 15 degrees aft are dead zones. And if you have wind from these directions, apparent wind, not true wind, then the rotors would not operate. So any other wind direction from the forward quarter, aft quarter beam of the ship is good wind that generates good thrust.
Okay, thanks, Nick. And then a commercial one. Can you give us an idea of what the sort of payback period for a rotor would typically be with those fuel savings?
So obviously the payback period for this technology is highly dependent on a number of factors, very closely linked with the price of fuel and the routes and the trading patterns of the ships. But typically there are payback periods for certain vessel types that come in well under the 5-year period. But again, it's very variable, dependent on trading patterns, vessel type, configuration chosen, and the price of fuel.
Excellent. Okay, thank you. Thank you very much for that, Nick. Thanks for really interesting presentation. We'll get ready to hand across to Siobhan now. And she's going to give us a presentation on cable design and analysis. So I'll hand across to you, Siobhan. Thanks. We'll just bear with Siobhan as she gets ready. I think your mute's still on, Siobhan.
Hi guys, can you hear me?
Yeah, that's great. Okay, over to you then, Siobhan.
Excellent. And you can see my presentation?
Yeah, I can see it fine. Thank you.
Perfect. Okay, so thanks for that. Sorry for the technical difficulty there. I am Siobhan, and my background is in designing and analysing subsea cables. And today I'm joined by my boss, Caroline Lowry, the analysis manager, and Mike Wells, the sales manager for the renewable cables that we provide. And they're here to help me answer any really tricky questions that you guys come up with during this presentation. So The subsea cables that you may be more familiar with are those associated with communication. So this is a map showing you all the interconnections between different countries where we do have communication cables in place. And you can see the majority of them follow the old shipping routes, but there's a staggering amount of subsea cables that are in the sea today. And we're talking about in the region of 1.2 million kilometers as of the end of last year. So the newer versions are obviously made using fiber optics for data transfer. So when we're talking about communication, we're talking about when you talk to someone on the phone internationally, or when you're searching the internet. These are the fiber optic cables that are being used to bring you information and to send information. So in general, when we put fiber optics underwater, they're very, very delicate. So we will armor them using these sections here, and we will put on a protective sheath layer here as well, and to give them a bit of reinforcement, stiffness, and protection overall. Now, the other type of cables, subsea cables that we have, are cables to bring us energy from offshore wind sources. Now, you may not be aware of this, but in the UK, we have a huge amount of offshore wind resource. So in fact, we've got the majority of the installed capacity for offshore wind in the world. We're closely followed by Germany and China is heavily investing, so they may overtake us at some point, but as of now, we have the most installed capacity, which is awesome. And you can see here, so for each of the turbines you have on a wind farm, you'll need inter-array cables that connect each of the pieces of equipment to the offshore substation, and then you'll need a cable from the offshore substation, which is called an export cable, to bring it back to shore for us to use. So you're probably familiar with these graphs from the news or the Met Ocean reports that you're used to seeing. This is an example of where all the wind farms are around the UK as of today. So you can see that we're taking advantage of a lot of the wind that crosses across our coastline and strategically placing these wind farms accordingly. Now, in terms of the energy that we're actually generating from offshore wind already, it's about 10% of all energy, electrical energy generated by the UK. And that 10%, which is up here, equates to being able to power over 30% of the UK households. So it's a staggering amount of energy that we're producing already. And if you look at where we were back in 2012, just generating 7%, we've increased that over 4 times to where we are today, so in less than a decade. So it's really promising to see how much energy that we're actually collecting on the single source of renewables. And this graph here shows you that with renewable sources and nuclear energy, all the primary energy, we're actually more than 50% of the UK electrical energy is generated through renewables and nuclear, which is excellent. So we're getting closer to that target that Nick mentioned about the zero carbon emissions by 2050. Now, we've been able to do that by adding more wind farms, but we've also been developing the equipment and systems so that we can capture more of the wind energy and bring that back to shore. So that involved increasing the size and complexity of these turbines to where we are today, which is about 9 megawatts. Now, to give you an idea of the scale, I've put in a local reference. So we've got Newcastle Tyne Bridge. One of these turbines, their rotor blade distance is about the same size as the Tyne Bridge. And in terms of the height, we're looking about 3 times the height of Monument, which is pretty staggering when you think about it, considering a lot of these are offshore. Now, as the turbines increase and we're generating more power, we need our cables to carry even more power. So we need to increase our voltage ratings of our cables so that we can carry essentially the increased power. So in order to provide these cables, JDR are leading the way in the UK by manufacturing hundreds of kilometres of renewable cables. We supply them generally here in the UK and in Europe and also around the world. So you can see that we've got the state-of-the-art facility here. You can see this is the Hartlepool Headlands. I'm not sure how many of you were familiar with JDR, but we're not too far away from your doorsteps, from those based in Teesside. And it's really useful having the vessels come up here to the dock. This is our factory here, so you can see it's quite large, and that means that we can manufacture very, very long lengths of cable and load them directly onto vessels as they're easily transported to where they need to be. Now, in terms of what the cables actually look like, we've got two main designs. We've got these static designs. So these are, you've got this power core components, you've got your fiber optic cable here, and you've got protective layer, protective armor wire layer here. Now these are static, so in general, the wind farms we've provided to have been closer to shore and coastal regions. So they are relatively short lengths, and we are able to have the wind turbine as a fixed structure in the seabed, and the connection point, or where the cable feeds into that wind turbine structure, is relatively close to the seabed. So the cable itself is relatively close and then sits on the seabed, which remains relatively static throughout its life. However, if you're in a scenario where you have a turbine with an cable entrance point that's a lot higher up, then what you'll find is you'll have a hanging length of cable down to the sea floor, and that hanging length is subjected to current and wave loading, which means that it will move quite a lot, and we will need to build in a bit more of a robust cable so that it can withstand that kind of fatigue motion that it's seeing, as well as providing us that energy. And that's why for dynamic cables you'll see a bit more armor, and it's contrahelically laid to give it a bit more torsional balance, and you'll have protective sheaths, so more abrasion protection with these as offered by these sheaths as well. In terms of size, we're talking about between 70 mil to about up to 120 or 200 mil, sorry. So that's about a range of just a bit bigger than a tennis ball up to about football or bowling ball size. So the size drastically varies, but the more we supply, the more we're seeing greater demands of power, and we're supplying cables in the larger ranges. Now, in terms of what goes into the conductor design, usually the conductors are stranded, and that gives the conductor a lot more flexibility rather than having a solid core. They're also made of copper or aluminium. Now, copper, as we know, highly conductive, which means that we can make the core quite small and still carry quite a lot of current. We've also got aluminium available. It's about roughly 60% as conductive, so we usually need slightly bigger cores if we're using aluminium as our conductor medium. Now, in terms of the insulation, okay, that's size based on the voltage that we're going to carry. So the majority of voltages, cables supplied at the moment are within the region of 33 kV, but we have developed cables that are capable of carrying up to 66 kilovolt voltage, and that's just shy of 300 times what you're getting out of your socket at home. So these are staggering quantities of energy that we're bringing back. And you'll have a metallic sheath as a basic component of your conductor, and that ensures that we have electrical stresses that are uniformly distributed radially around the conductor within the insulation, which is great. Okay, so in terms of transmission, when we're developing these larger and larger sizes of power cores, and when we're talking about large sizes at the actual core itself, if you look at most of the wires around your house or your lighting or your charger at home, they'll probably have a sort of 1.5 millimeter squared conductor inside them. Maybe 2.5 if you're looking at something that gives you a bit of power. The conductor sizes that we're talking about for floating wind are up to 1,000 millimeters squared. So that puts a bit of perspective in how large we're talking. But as we increase the size of the conductor, what we see is we've got to account for the skin effect. So when we're applying when we have current flowing through a conductor, the resultant magnetic field forces the electrons towards the outside of the conductor, which increases the resistance and the inductance. And that's in a single core. So you can see there the current density is quite high around the edge of the conductor. And when you have two conductors in proximity to each other, you also have this effect where you have the change in the densities. Instead of going fully away round, they're affected, and you can see they're interacting with each other. So this is what we see in our press oil cables, or our 3-core cables. You'll see the electrical density up here is quite high, and there's very little current traveling through this central section. So that's something to be aware of in terms of how we size the central conductors in each of the energy cables that we use. Okay. In terms of the insulation layer, which we know is sized in voltage, we need to make sure that we can minimize the electrical stress. So that's the volts per meter inside the cable. And it's highly dependent on geometry. So if we have a stranded conductor, conductor is this shape here. And if we extrude insulation straight over the top, what we end up with is this geometry change where the curvature is changing, and we get this massive peak of voltage. So that's what we want to avoid at all costs. We want a nice uniform set. So what we do is we put in this extra layer on either side of the insulation, and this layer is applied over the conductor, and you can see there, and it offers a very smooth surface for the insulation layer, which is here to go on. So this layer and this layer is semiconducting, and we apply them in a triple extrusion operation. So what we could do is, if we had a power core, we could apply this in one operation, then in this in another operation, and then this in another operation, so stagger them out. However, we want the insulation layer is critical in a power core, so we want to ensure that there's minimal chance of any contamination getting into that 3 sections as possible. So what we do is we apply it through this triple extrusion method, which means that the 3 layers are applied in one operation, similarly to how toothpaste is produced. Okay. Right, now in terms of putting cables underwater, most of us will know that water permeates through plastic. It's an unfortunate fact, but it's one that we need to deal with. So we've got multiple different designs that we can offer, and that is known in industry. Now, what we could do is put some sort of metallic barrier, and that's what these 2 designs are about. So you might have a metallic corrugated layer over the core, or you might have a lead extruded jacket. Now, both of those are there to try and fully enclose the cable and prevent water from permeating through. However, they're very, very large, and they're quite stiff, as you can imagine. So we look at different ways where we can minimize or mitigate against water permeation through, and we'll play around with the layers that we apply. And the selection of the layers in a core is dependent on the situation it's going in. So we could put various sheathing arrangements instead, or combine it with some kind of foil arrangement. Now, when we're talking about foil, we're talking about foil that's extremely thin. So if you think of oven foil at home, it's that kind of thickness that we're applying to our cores. And what we'll do is we'll overlap that foil, and we'll glue that section. So what we'll try and do is make the overlap incredibly large. And what that does is it makes it more difficult for the water, because it has to permeate all the way through this layer before it can get through here. And we can predict times of that. So that's the reason why we would varied designs. And a smaller design generally results in a more flexible conductor, which means we can provide a more flexible cable, which means it's easy to install and handle and transport. Okay, so we also need to worry about cable temperatures. So when we're using anything that it was drawing a high amount of power through it, obviously there's a propensity for that to heat up. So what we'll do, we can do it through computational modeling, but we'll also, if we've got a tricky scenario, we will look at doing some FEA modeling, especially if we've got some other heat source in the environment. And what we can do is we can put current through these conductors and predict how hot the outside of the cable is going to get, and predict how heat is distributing through this area, depending on, of course, the environmental temperature around it. If we get a collection of cables together, you may find that there is a heat that builds up because they don't have as much heat dissipation. And that's very similar to when you buy a very long extension cord, for example, like a caravan, and you need to you're going to use it to draw a lot of power through it, to power your caravan for a long period. Most of the manufacturers will say you need to uncoil or unravel that cable to ensure this kind of heating effect doesn't occur. And there have been several incidents where that hasn't taken place, and there have been incidents of fires. So that's something to be aware of when dealing with any kind of electrical cable, to manage the heat dissipation. Okay, now in terms of how we build the cables themselves, we want to twist up our conductors, and we're applying the twist so that the conductors form a sort of helical structure within the bundle. And the reason we do that is to try and equalize the tension and compression that is seen when we bend the cable in its entirety. So you can see here, if we bend it around quite a large OD, really, this section or this component would see a lot of compression, and this section would see a lot of tension. So we try and equalize that out so that the tension and compression is balanced out. And it means we can bend the cable to a much smaller diameter without having any issues with the components. So if you think about it, if you thought about a runner, two runners running next to each other, this guy has to run a lot further around this track than this guy. If we put them on this path, they both sort of share and probably both going to meet at this point at similar times if they run at similar speeds. Okay. How we actually apply that, we've got these massive machines in Hartlepool at our manufacturing site. So putting a big power cores on these massive drums, which are about 60 tons in terms of capability. And they rotate around their own axis. And this carousel rotates around this central section. So it's rather like planets rotating around the sun. So this rotation is happening so that we can put these components up through this die plate here and twist them into the bundle. We want to twist these sections to make sure that it's straight in this. After we've assembled the bundle, we'll apply armor, and you can see that is also helically wound onto the bundle. And we'll apply either sheathing or rovings, as you can see. In terms of installation, we've come a long way from what it used to look like. These guys, you can see, you've got a raft or a jimmy raft stuck together, and you've got, these guys are doing quite a good job of really trying to monitor the tension or manage the tension of this cable as they pass it over. Considering the technology at the time, that's pretty decent, but we've come a very, very long way since then. So not only can we map the seabed and monitor the cable as it's being laid, but the tension control is very different. So if we have a cable stored on this section here, we now have very controlled tension as we lay this cable out. And that matters so that we can balance how the cable is being laid over the surface and ensure that we don't damage our cables. Right, so in terms of developments as we're going forward, I mentioned that we had dynamic cables, and they were required when you had a gap between the seabed and the entrance to a floating structure, such as a wind turbine. As we progress in wind farm development, we're trying to harness energy that's a lot further out, because the wind speeds further out to sea are a lot greater, and we've got these gigantic turbines that we're now producing. So the floating structure is usually moored with these big anchor lines, and we have to attach our cables somewhere in here so that it can be connected to the grid. So in this position, as it's moored, the floating structure can move. So we need to be able to make sure that when it's in its furthest position from the cable touchdown point, which is here, the cable length is still enough that it has enough pliability to be able to flex with the loading and minimize fatigue within that section and minimize tension. However, when the floating structure moves back, we also need to make sure that we can manage the length that was needed as it's all bunching up now. So we apply these little buoyancy modules, and that gives us a bit of thrust. However, buoyancy modules lose a little bit of their buoyancy over the lifetime of the product, so we'll also model the buoyancy at the end of the life condition, which is 20 to 30 years. And we want to make sure that the cable is not going to hit or disrupt the seabed on this section. So it remains intact in both conditions, the start and end of life. So, and that's where we're going through with cables and the new exciting challenges that we're seeing at the moment. Does anyone have any questions?
Excellent. Thank you very much for that, Siobhan. That was, again, really interesting. There's a few questions that have come through, but quite a few of them I think you answered in your presentation. One of the questions that we had was to do with the core material. So somebody asked, what applications have you used aluminium cores for, and why were they chosen over copper? Okay, so that is a good question. We have used aluminium cables in renewable energy wind farms. They're usually chosen by the client after we've come up with our concept designs. The main reasons why they're different, copper is often heavier. Although you're using less of it, it is often heavier. And aluminium, the price of aluminium does fluctuate with respect to copper. So it can be cheaper to go use an aluminium version in terms of actually buying a product. But both power core designs with both different designs of core will look slightly different because of the materials that we've selected. Okay, thank you. So somebody's asking a question about testing in-house, specifically about partial discharge testing. Can you maybe give us a bit of an overview about the testing process for your cables? Yeah, so the testing process for the cables are to strict standards, international standards. Partial discharge testing is very fun, but essentially the requirements for the partial discharge testing are within set international guidelines. So we will always conduct tests as per the requirements in those, in order to make sure that we have reliability across our product and variability. Okay, thank you. There's a couple of questions about the lifetime of the cable, which I think you said was sort of 25 to 30 years. That is pretty typical. People are asking, can it be recovered and can it be recycled? Yes. So as part of the decommissioning plans, the developer of the wind farm site can recover its cables. That is definitely an option. And for cable lengths that we actually use in-house to, as part of the process during manufacture, you will use little bits of the cable off the ends in producing the final product, and those we recycle as well. So they are recyclable, and I guess the wind farm developers will be able to select what they do with them.
Yeah, with all, sorry, it's Mike Wells at JDR here. With all of the offshore wind farms, there'll be a decommissioning plan, which establishes how they will recover the cables. But basically, at the end of the wind farm lifetime, they've got to leave the seabed in as close to original condition as possible. So they've got to decommission the cables as well.
Okay, thanks. And just one final, I'll take one final technical one. Someone's asking what kind of material the insulation's made from?
That is a good question. So land cables are usually made from like oil pregnated paper insulation. However, and that's worked really well for static land cables. However, they do have a temperature limit and they aren't as flexible. So there was a progression onto EPR, ethylene propylene rubber, and that is quite good. It's quite heavy though, and it can be a little bit more expensive. So we've transitioned on to XLPE. So that's typically what is built in cables today.
Excellent. Okay, thank you for that, Siobhan. Thanks for the fantastic presentation. So we'll just bring tonight's webinar to a close. Just like to say thank you again to Nick and Siobhan for their presentations. And just a reminder that we'll be having our fourth Tech Talk event on the 27th of May at 5:15, which is going to cover the Subsea offshore wind farm and the Teesside net zero carbon capture and storage project. So hopefully we'll be able to see you then again. Okay, so thank you very much.